Good morning, everyone. I am happy to present before you our study design and analysis of optical sensor for detection of cancer biomarkers conducted by Harshada J. Patel, Raksha DS, Ashwini VR, Indumati TS, Preeta Sharan and myself Rohit DH. The proposed paper incorporates the modeling and simulation of the highly sensitive photonic crystal-based sensor for the breast cancer as well as the cervical cancer infected cell detection. For the detection of cancer-infected cells, the change in the refractive index is considered as the basis and the corresponding change in the properties of the light rays is observed. And this study have been discussed under the different slides proceeding from introduction, surveys of methods and different topologies, hexagonal shape for the breast cancer, 180-degree phase mismatched hexagon for the breast cancer, hexagon shape for the cervical cancer and 180-degree phase mismatch for the cervical cancer and the conclusion. So let's begin with the introduction. Standard test for the breast cancer test is the mammography and for the cervical cancer is the pap smear. Looking at the disadvantages of both the tests, the proposed photonic crystal sensor can be benchmarked with respect to cost and the testing procedures. The working of this proposed sensor is similar to the ionic lattice effect on electrons in the solids. In the same way, the periodic optical nanostructure, the photonic crystal affects the photon movement. Electromagnetic propagation is affected by the protonic crystal, which creates the band gap in the layers of periodic dielectric nanostructures. The refractive index values of the normal cell as well as the cancerous cell will be predetermined and it is used to benchmark for further comparison. The cells that have been used for the study of cancer affected cell and the normal cell condition has the refractive index as shown in this table. Now we will see the hexagonal shape for the breast cancer, analysis of the hexagonal shape for the breast cancer. For this, we analyzed this using the FTDD software. Okay, and here is the designing part of the hexagonal shape. And this is the observation area, and here we can see the hexagonal shape. Okay, and we need to analyze the transmission of the light through this hexagonal model. And here is the breast cancer cell properties, that is the RI value of the breast cancer cells is the 1.3999. And by simulating this, we will see, I'm going to simulate this. This is the observation area. Yeah, I'm running this and okay, here we will get the simulation result. Okay, yeah, this is the observation area and this is the transmission of the light rays through that hexagonal model. So here we can see the movement of the light rays for the normal cell and this is for the cancerous cell that we can see from that simulation. So by careful observing this graphs, we can say that the peak value of the normal cell graph corresponds to the value of the 12.31 and that of the cancer cell is 17.84. So this makes the clear difference between the normal cell and the cancerous cell. The red color represents the normal cell and the green color lines represents for the cancerous cells. and the sensitivity can be found by using the lambda 1 minus lambda naught divided by eta 1 minus eta naught, and the sensitivity for the hexagonal shape of breast cancer is found to be 2.0134. Then let's move into the 180-degree phase mismatched hexagon for breast cancer. And here also we did the same simulation for the 180-degree phase mismatched structure. And this is the result of the movement of the light rays for the normal cell, and this is for the cancerous cells. And here when we plot the graph of relative power of normal cell versus a cancerous cell, we can see from the graph that the peak value of the normal cell graph corresponds to the value of 1.69, and that of the cancer cell is 13.24. So this makes the clear difference between the normal cell and the cancerous cell. And the sensitivity of 180-degree phase mismatched hexagon for the breast cancer is found to be 0.6711. Then in the same way we did for the cervical cancer. And the cervical cancer, this is the hexagonal model for the cervical cancer, and here we use the refractive index of the cervical cancerous cells and the normal cell. So this is the result of the movement of the light rays for the normal cell, and this is for the cancerous cell of the cervical cancer. And here we can see the peak value of the normal cell graph corresponds to the value of 12.47, and that of the cervical cancerous cell corresponds to 8.69. So this also makes the clear difference between the normal cell as well as the cancerous cells. And this is the 180-degree phase mismatch for the cervical cancer analysis. So here we created the 180-degree phase mismatch structures and of the FTDD, and this is the result of the movement of the light rays for the normal cell, and this is for the cancerous cell. So by the analysis of this graph we can observe that the wavelength shift is high in this structure, that is the wavelength shift is high in the 180-degree phase mismatch structure. Henceforth, this structure we can consider as the most sensitive for the detection of cervical cancer affected cells against the normal cell. And here the sensitivity is found to be 4.116. So let's move into the conclusion. The observation made here is that the sensitivity of the cells has changed drastically. By applying this technique, it can be easily distinguishable between the normal cell as well as the cancer cell condition. In this paper, the comparative study has been done for the sensitivity by considering hexagonal and 180-degree phase mismatch. After the sensitivity calculation, it is observed for cervical cancer detection, 180-degree phase mismatch structure is better, and its sensitivity is 4166 nanometer per refractive index unit compared to the hexagonal shape having the sensitivity of 1250 nanometer per refractive index unit. That means the 180-degree phase mismatch structure has the more sensitivity and it is the better one. So for the breast cancer, hexagonal structure is better with the sensitivity of 2013 nanometer per refractive index unit compared with the 180-degree phase mismatch having the sensitivity of 671 nanometer per refractive index unit. That means for the breast cancer, we have to consider the hexagonal structure is the better because it has the more sensitivity. So these are all the references, and thank you for providing such a good opportunity. Thank you.